Okay. So a short summary of my presentation. We use the fuse deposition modeling to print some specimens in order to investigate the notch and size effect. We did the tensile and fracture toughness static test, and then we try to apply the theory of critical distance in order to investigate the notch effect. I will not stay too much on the fuse deposition modeling. It's a now very often used additive manufacturing technique due to its advantages, because it became very low cost, but has advantages that it could produce very complex shape of the components. But on the other side, we have some problems with the integrity and durability of such components. Also, it is very important to understand the influence of the manufacturing parameters on the mechanical properties of such structures. And on particular, it is very important because we use to print and to design very complex shapes, we need to take into account the notch effect for this and the size effect. So very shortly, so we have a polymeric filament, which is forced to go through an extruder. Then it's arrive in a heater block, it's melted, and then through a nozzle is deposited to a plate of the machine. There are many applications, and there are many studies on the mechanical properties of this. However, there are not so many studies on fracture toughness of these materials. There is probably one of the first paper is a group of Mountain University on Leuven. Professor Pinter is here. So they investigate the fracture toughness and fatty crack propagation for PLA materials using single edge notch bend specimen and compact tension specimens, and the values were around 5 to 6 megapascal square meters. Also, there are some studies on ABS and PLA reinforced with carbon fibers to determine the mode 1 and mode 2 fracture toughness. And there is an attempt done by Professor Susmel in UK. He used the equivalent homogenization material with theory of critical distance and for PLA, and having the ultimate tensile strength and the fracture toughness of PLA, he estimated a critical distance of 4.8 millimeter, and this was applied after that for several geometries of notched and cracked specimens. So what we did, we use polyethylene tetraplat glycol. We have here the parameters for printing. We use a Prusa printer. We use 100% fill. The specimens were all manufactured on the plane, so on the plane of the desk of the printer, and we use a rectilinear plus minus 45 degrees for the filling the forms. First tests were tensile strength, static tensile strength test. These were done in our click testing machine. We use a clip-on extensometer for determining the Young modulus. We did all our tests at room temperature and with a loading speed of 2 millimeters per minute, and we use dog-borne specimens. So the value for this PET material was the value of the ultimate tensile strength was around 41 megapascals. Then we determined the fracture toughness. We use 6 single edge notch bend specimens with the same, let's say, room temperature and loading speed. We use the standard for fracture toughness determination of plastic materials because there are no standards specific for additive manufacturing materials. And we get 5 megapascal square meter the value of the fracture toughness. So with these values, we try to estimate the critical distance using the point method, as was defined by Professor Taylor using an asymptotic matching. And, our specimens were three types of specimens: V-notch, and two specimens with rounded notch of 0.8 millimeter and 2.2 millimeter the notch radius. We use 3-point band, symmetric 3-point band test, and we did the experiment in order to investigate also the size effect on different size specimens. So we use semicircular band specimens with 10, 20, 30, and 40 millimeters. We use a ratio of 0.5 between notch length and radius, and all the specimens were with the same thickness of 6 millimeters. We perform a linear elastic fracture analysis in order to get the distribution of the maximum principal stress. And with this distribution, we determine at critical length over 2, we determine the maximum principal stress. And with this value, we predict the load which should be applied to break the specimen, taking into account the ultimate tensile strength of the material. So some of the results. So we have here the effect of crack length. So we have different lengths of the crack, and the ratio between crack and R radius is here between 0.25 to 0.55. What we can see that our predicted values are in the range of plus minus 15% up to crack length of 0.5. Bigger cracks, so the predictions are far from the experimental values that we get. On the same time, we want to look on the ligament side, so use as a parameter the ligament size divided by the critical length, and we see here that the TCD is valid when the length is double of the critical distance. Below this value, so the prediction is far from the experimental value. We also the theory of critical distance to other or to different manufacturing parameters. So we change the in-time orientation of the specimen, 0 for the previous result and 45 degrees. And we use two different filaments, color of the filaments, white filament and burgundy filament. And we can see that the predictions are quite well. We use the same value for the that was determined on the white specimens for the fracture toughness and for the ultimate tensile strength. So probably so the predictions could be improved is if we use or we try to determine tensile strength and the fracture toughness for each type of, let's say, set of material filament, and for each set of the manufacturing parameters. So to conclude, so we investigate the notch effect on PET specimens obtained via FDM. We use semicircular band specimens loaded in 3-point band symmetric load. We determine the ultimate tensile strength, the fracture toughness, and we got a value of 4.78 millimeters, the value of the critical distance. Theory of critical distance looks to be valid for crack lengths up to half of the radius, and for ligament higher 2 times higher than the critical size. So I need to acknowledge the project, the East European Twinning on Cultural Integrity, the project that financed its research. And finally, I would like to invite you, some of you already submit a paper, so we have the final conference of this project, which will be in beginning of March, and from 16th of February, Timișoara is European Capital of Culture. So I invite all of you, probably for this conference or maybe with other occasion, through 2023, we are the European